Welcome to the Explainer. So, have you ever wondered how AI actually comes to life? I mean, beyond all the math. Today, our goal is incredibly exciting. We are taking all that abstract neural network theory we've been talking about and transforming it into a real-world Python-coded reality. And to do that, we're going to be using TensorFlow, which is literally one of the world's most popular deep learning frameworks, alongside Keras. Keras is fantastic because it gives us this brilliant, high-level interface so we can build these networks without having to write hundreds of lines of really complex, tedious math code.
Okay, let's dive into this. We're making a massive shift right now. We're moving from the whiteboard of theoretical concepts straight into a practical builder's blueprint. I mean, the theory is absolutely essential, for sure. It tells us how these networks mimic human learning. But the programming, that is where the magic actually happens. It's how researchers and engineers are out there actively deploying these systems in healthcare, finance, and climate science today. So, here's our roadmap for today. First, we'll cover building the neural network, then training the model, moving beyond basic accuracy, unpacking the confusion matrix, improving and comparing models, and finally, looking at the next frontier. All right, section 1, building the neural network. Before we can even touch TensorFlow, we have to prep our data. Think of this as laying the foundation of our house. First, we load our data. We're going to use our wildfire dataset as an example today, where we look at things like temperature, humidity, and wind speed to predict the risk of high PM 2.5 pollution. Next, we split the data. We have to keep a testing set completely hidden away so we can test the model on truly unseen data later. And finally, and honestly, this is a step so many beginners completely miss, we scale the features. Neural networks just perform so much better when numerical features are standardized. But here's the absolute critical part. We fit our standard scaler only on the training data and then apply it to the test data. If we fit it on everything all at once, well, information from the test set leaks right into our training process, and that completely invalidates our results. We definitely don't want that. Once the data is ready to go, we build the actual brain. You can think of this architecture like a funnel. It acts as a really powerful pattern recognition engine. So the data enters the input layer. Then it hits the first hidden layer, which has 32 fully connected neurons using the ReLU activation function. This layer is basically learning the simple patterns. Then it funnels down into a second hidden layer of 16 ReLU neurons, which takes those simple patterns and combines them into much more complex representations. Finally, it narrows all the way down to a single output layer neuron using a sigmoid activation function. And that single neuron just spits out a probability between 0 and 1, cleanly classifying whether we're looking at a high or low risk for wildfire pollution.
Moving right along to section 2, training the model.
Let's move to and see how this builds, because now that our architecture is defined, we actually have to bring it to life through training. When we hit train, the model processes the dataset in cycles, which we call epochs. In just one single epoch, the training data moves through the network in forward propagation to make a prediction. Then our loss function, specifically binary cross entropy here, since we're just deciding between two outcomes, calculates exactly how wrong that prediction was. After that, backpropagation sends that error backward through the network, and the Atom optimizer jumps in to efficiently update the weights of our neurons to make them just a little bit smarter. This exact sequence repeats, say, 50 times over 50 epochs, constantly learning and adjusting the whole way through.
Okay, section 3, beyond basic accuracy.
And this brilliantly illustrates a huge point. So the model is trained, and maybe it says it's 95% accurate. Time to celebrate, right? Well, actually, not exactly. This is exactly why professional researchers never just look at a basic accuracy score. Let's imagine two doctors, and they're both diagnosing 100 patients. Dr. A gets 95 right, but misses 5 totally life-threatening diseases. Dr. B also gets 95 right, but only misses 5 really minor illnesses. Now, both of them are technically 95% accurate on paper, but clearly their real-world performance and the actual consequences of their mistakes are entirely different. The exact same principle applies to our neural networks. Accuracy alone simply does not tell the whole story.
Which brings us to section 4, the confusion matrix.
To truly unpack the real story behind our model's accuracy, professionals rely on a specific tool called the confusion matrix. It essentially breaks our predictions down into a 2x2 grid. You've got your true positives and true negatives. That's where the model nailed it and got it right. Then you have false positives, which is basically a false alarm, but I want to highlight the false negative quadrant here. Let's anchor this abstract math to a really high-stakes scenario. Suppose a wildfire actually causes dangerous PM 2.5 pollution, but our neural network predicts low risk. That's a false negative. Because of that, emergency responders fail to issue warnings, and you are literally putting lives in danger. In a lot of real-world applications, minimizing that false negative is far, far more important than just bumping up some overall accuracy score. This grid is great because it allows us to extract some really vital metrics. First up is precision. Precision asks the hard question. When the model actually raises the alarm and predicts a positive case, how often is it right? High precision means virtually no false alarms. It means people can actually trust the warning. When the model says something is happening, it really, truly is. The second critical metric here is recall. Recall asks a slightly different question. Out of all the actual positive cases that happened in reality, how many did the model successfully detect? Let's connect this back to the sports biomechanics research we've looked at. If you're using motion capture and force plates to detect an abnormal, injury-prone gait in a patient, a false negative means sending an injured person home with zero treatment. In healthcare scenarios exactly like this one, achieving high recall is absolutely vital, because missing those true cases has very serious consequences. Now, sometimes you find yourself in a really tricky situation where you need both high precision and high recall at the exact same time. You can't afford false alarms, but you also absolutely can't afford to miss anything. That is exactly where the F1 score comes in. It's a single, balanced metric that combines both mathematically. It is the go-to score when you really want to measure the overall harmony and true reliability of your model's predictions. Let's jump to section 5, improving and comparing models. So the crucial point is, once we've evaluated the model and found its weak spots, how do we actually make it better? We usually start by evaluating its overall performance across lots of different thresholds, using what's called the ROC curve, and more specifically, the area under the curve, or AUC. The AUC gives us this incredibly useful single grading scale for how well the model actually discriminates between classes. An AUC of 0.50, that means the model is just randomly guessing. 0.70 to 0.80 is fair. But when you push that number above 0.90, you have an absolutely excellent model on your hands. It just beautifully summarizes the overall classification power in one number. Now, if your AUC isn't quite where you want it to be, you turn to hyperparameter tuning. Unlike the internal weights that the model naturally learns during training, hyperparameters are the foundational structural settings you have to choose before training even begins. Things like, how fast should it learn? How many hidden layers do we need? How many neurons? What's the best batch size? And professionals, they don't just sit around and guess these. They use automated methods like grid search or Bayesian optimization to systematically test combinations of these variables. That is how you seriously level up a model's performance. Now, what's really interesting about this slide is the ultimate test, our algorithm showdown. Once our neural network is completely tuned, we compare it against other models for predicting that wildfire PM2.5 risk. Look closely at the numbers here. Our artificial neural network is fantastic, sitting at 91% accuracy and an AUC of 0.95. But notice that XGBoost actually slightly outperforms it with a 92% accuracy and a 0.96 AUC. This is a massive lesson for anyone in data science. Despite how incredibly powerful neural networks are, there's just no universally perfect algorithm. On highly structured tabular data, like rows and columns of weather metrics, tree-based models like XGBoost can absolutely give neural networks a serious run for their money. Finally, section 6, the next frontier. We've seen exactly how to build, train, evaluate, and tune our neural network today, and it's incredibly powerful for the kind of tabular data we've been using. But as we look forward, we face a pretty major structural limitation regarding exactly how data is fed into the system. Traditional artificial neural networks treat every single input entirely independently. And hey, that works great for a spreadsheet of weather data. But imagine trying to feed a photograph into this network. We would essentially have to flatten a 2D image into one giant single-file line of pixels. When we do that, we completely destroy the local spatial relationships. The network has absolutely no idea that a pixel was right next to another pixel, forming a curve or an edge or a shape. Structurally speaking, the ANNs we've built today really struggle to comprehend visual reality, which leaves us with a massive question to ponder. If traditional neural networks ruin spatial data by treating every input independently, how on earth do modern AI systems actually process medical imaging, or drive autonomous cars, or even recognize our faces? Well, the answer to that lies in an entirely different architecture, one that's actually inspired by the human visual cortex. But that is a journey into convolutional neural networks for our next explainer. Thanks so much for joining me today, and keep building.